All right, hello everybody, and welcome to our second guest lecture of this quarter. Today we're going to be having Dr. and soon to be in a couple months, Professor Dixit, who got her PhD at Caltech, is that right, with Joel Burdick, and then has been working with Professor Aniruddha Majumdar at Princeton, and then will be starting as an assistant professor at UCLA this summer. Professor Dixit is interested in uncertainty quantification for learned and black box models, which is a very, very important area of research right now. And today we'll be talking about this for two very popular application areas, which is both on the perception models for planning, as well as on large language models for uncertainty quantification in LLM-based planners. So with that, Professor Dixit has said that the best thing is to ask questions during the talk. And so you can feel free to do the little hand raise thing, and I'll stop and you can ask your question, or you can ask the question in the chat and then I will just verbally say it out loud. But with that, take it away. Thank you so much.
Great. Thanks for the introduction, Sylvia. As Professor Herbert said, I will be discussing a technique, it's called conformal prediction for uncertainty quantification for robotic systems. And it's becoming really popular. So I want to focus on how to think about applying these uncertainty quantification techniques, but with like robotic applications in mind. So a little bit of motivation. We've of course seen robots perform really complex tasks in different kinds of environments. So the first video you're going to see here is of Tesla Autopilot. So this is a Tesla Autopilot running in a suburban environment, and it's able to totally autonomously navigate through this environment. And as you can see on the side, using its different cameras, it's able to detect all of these different cars, sometimes bicyclists and everything in the environment, and navigate really well. The next video that I'm going to show you is from Google DeepMind, from their work called SECAN. And here, what we have is a robot being given a language instruction. So in this case, the video might be hanging. Let me pause this. Yeah. So the user input is, oh, I spilled my Coke on the table. Can you bring something to clean it up and then throw away the Coke? And here what you see is the robot is able to interpret this human instruction using a language model. So there's a language interpretation of it, and there's also an interpretation of what are the possible tasks that the robot itself can perform. So that's what the affordance is. And then it is able to combine these different language scores and this affordance of what it can actually do, given this language instruction, and then perform all of these different tasks. So first it finds the Coke can, then it picks it up, goes to the trash can, and then finds a sponge for the user to clean up the spilled Coke, which is really amazing because now we have this robot that's able to actually interpret a human instruction and do this various set of tasks totally autonomously. So this is really amazing. But I would argue that these systems are still not totally reliable. So here I have, again, the Tesla Autopilot that's running in this environment that has been set up by this YouTuber. But really what happens is it first runs through the yellow tape, and then next there's a fake child and dog on the path that it hits, and unfortunately it runs over. So this is totally unsafe, and this is a failure of its perception system to be able to avoid, to not be able to avoid collisions in time. The second thing that you're going to see is, again, one of these SECAN videos that I showed you earlier as well. But now the instruction here is I left out a Coke, apple, and a water. Can you throw them away and then bring me a sponge? So far, the robot has put away the apple, it's put away the bottle of water near the trash can. The next thing that it's decided to do is find a Pepsi. But that's not actually the user instruction. The user instruction is to find a Coke, right? So it takes up the Pepsi and it is able to correctly throw it away, but that's not exactly the instruction that it's really been given here. So this is an error in the interpretation by your language model. You may say that, well, this Tesla setup is kind of manufactured, but this is really happening in the real world. This has happened with Cruise. Late last year, there was an incident where there was a Cruise driverless car that hit and dragged a pedestrian, and then it had to recall all of its driverless cars because it had to update its collision detection system. But we really don't want this happening on systems that are really running in the real world and can cause a lot of damage. We also actually tried a similar setup with the GPT-3, where we told GPT, hey, could you pick up the bowl and put it in the microwave? But as you can see here, there are two bowls. There's a metal bowl and a plastic bowl. And so we asked GPT, which bowl would you pick up? And GPT very confidently says, I will pick up the metal bowl as it's more likely to be able to withstand the heat from the microwave without melting or getting damaged. But you don't want to put a metal bowl in a microwave, and that's really dangerous as well. So these are real tasks that you may see a robot trying to do in maybe a household setting or even in autonomous driving settings, where you want them to be very reliable. Are there any
There's a question in the chat. Yeah.
Yes.
The second case, the LLM case, can this be considered as a failure in terms of safety? Is this a safety critical?
I would say so. I would not want metal bowls in my microwave, but I would like to be able to rely on a robot and not have to babysit it all the time to check which one it is. But you could also say that there is some ambiguity in the human command here. You could say that the human really also wasn't clear which bowl to pick up, but that happens all the time. You know,
Sorry
human
to
instructions
interrupt, but I was talking about the case where the robot picks up the Pepsi instead of the Coke.
Yeah, it's not really safety critical. It's just an LLM mistake. So which is why I was showing this example, exactly like you said, to illustrate that this could quickly also become safety critical.
Okay.
Yeah, totally. It doesn't matter. I'd just be a little upset if it threw away my Pepsi instead of Coke, but it doesn't. It's not really that safety critical. Absolutely. Yeah. Any other questions? Okay. So the question that I want to ask today is, how can we guarantee that our robots that we interact with are reliable in new, potentially unseen environments? Okay, so here I have a very simplified robot autonomy stack, where the human is giving an instruction, the same one that we've seen before, put the bowl in the microwave. The robot maybe uses an LLM to plan to the bowl in the kitchen. While doing so, it's also perceiving its environment, where it's trying to figure out where things are. And then given what it sees in the environment, it takes some actions and hopefully succeeds in doing the right thing. As I said, LLMs, if we use that to interpret the human instruction, can have errors in what they think is the right next step to do. So in this case, you can have a plastic bowl or a metal bowl, and then the robot puts the metal bowl in the microwave, and that leads to a pretty safety critical failure. Alternatively, another thing that could fail in this autonomy stack is that you could maybe use a transformer model or something, a neural network, to perceive your environment. So this is something off the shelf that you're using. Maybe you're trying to navigate through, maybe the robot is trying to navigate through this environment where you have a couple of chairs and futons, and you want to not collide with these chairs, right? But as you can see here, the red boxes are the output from an off-the-shelf perception model. And the blue boxes are the true locations of our objects. You can see what the robot is seeing in this case, which is the 3D point cloud that we've constructed. You can see there are quite a few occlusions over here, where this chair is not totally visible. This futon is also only half visible. Any of these things can really lead to perception errors where the outputs of our pre-trained systems may not be exactly right. And that can lead to some failure downstream, even if you're using a planner that's totally safe. Right. Okay, so for these kinds of learned models, we want to do uncertainty quantification. A lot of times these learned models often have heuristic or sometimes no notion of uncertainty. Another thing that happens when we're using or deploying these learned models on our autonomous systems is that the environments that we deploy these models in may be totally different from the data set that these models have been trained on, right? So here again, I have a Tesla car that's interpreting the setting sun incorrectly as a yellow light in the middle of the road. And lastly, this is a more subtle point that I'll get back to later, but the robot actions and the resulting closed loop behavior of the robot may actually also lead to a different distribution of states and a different distribution of observations than what the learned model has previously seen, right? So there are quite some ways, classical ways to account for uncertainty. And maybe you've seen some of these before. One, you could assume that it has like a Gaussian nature. And then what you could choose to do is say that, okay, with probability, say 1 minus alpha, my uncertainty is going to lie within some set, since I know that my uncertainty is Gaussian. The other thing that you could also do is maybe you know that the uncertainty is bounded. Then you account for all possible uncertainties within this bounded set, and then account for that as well. The common theme in both of these cases is that you have a prediction set, and which is what we also want to do in this case. We want to predict a set with our learned model output, such that the true label or what actually ends up happening, the true prediction will lie within the set with some user-defined probability that you can choose. But we can't assume, of course, that the nature of this uncertainty is Gaussian or bounded. We actually don't know anything about the kind of uncertainty that these learned models will have. So what we aim to do today is to represent this uncertainty using prediction sets, and we have a probabilistic nature for these prediction sets. And I want to look at two applications for this. I want to look at uncertainty quantification and finding these prediction sets for regression models, as well as classification models. So in this case, I'm just illustrating this via like a simple linear regressor, and you want this orange uncertainty set such that your prediction set such that you know that the true label, these true green points that you're seeing, the occurrences, lie within this orange set with some probability. For a classification module, maybe you have some learned classifier that's able to distinguish, again, very simple here, between these two classes. You want to have some notion of uncertainty such that you have a prediction set, such that maybe for some of these points, you're not totally sure if it's in the green class or the red class. And so you want to say, oh, it could be either one of these. And we want to figure out what's the technique using which we could do this. I also very quickly want to talk about when these prediction sets are useful for the kind of applications we care about for autonomous systems. for regression, for example. You can consider maybe you're in an environment where you have dynamically moving obstacles. In this case, maybe you want to predict the trajectory of a ball that's been thrown around. And you want the robot or the autonomous system to be able to avoid it, right? You could potentially make these point predictions of where the ball is going to end up. But really, what you would like to do is also say, okay, it's going to end up within this yellow region somewhere over time. You want to be able to account for that in your autonomous step. Similarly, like I said before, you could have an off-the-shelf object detection module that's predicting these red locations of the obstacles, but you want to somehow process these outputs and get these potentially larger blue sets that you're seeing within which your true obstacle is guaranteed to lie. You can also take the perspective of having dynamics uncertainty, right? Maybe your dynamics are uncertain. You want your system to go from this position, maybe to this ZXF, this final position. And you want the system to be able to do that successfully. Again, if there's some uncertainty in your dynamics, you want to predict a set within which you want to travel so that the robot can eventually reach the set XF. Let's also talk about when these prediction sets are useful for classifiers. I have a really silly example that I really like, where you're trying to distinguish between a chihuahua and a muffin, right? Maybe in some images, you're totally, the classifier is totally sure that it's either a chihuahua or muffin. Go ahead and predict that very confidently. But if in some images it's not sure, then maybe you want to say, oh, it could be either. I'm not sure. A more concrete application of this for autonomous systems is in self-driving, right? You could have a pedestrian versus a bicyclist. Both of them are going at different potentially speeds. If you're not sure if it's a pedestrian or a bicyclist, you want to be able to account for both of these motions. But if you are sure, then your autonomous car can account for whichever one it is. And as I showed before, if you have a language instruction, for instance, of like, oh, I spilled my drink, can you help? And the language interpretation of that gives you multiple possible options. The most likely being find a cleaner, try using a vacuum, pick up a sponge. And then there are some more likely than others options of find a sponge, go to the trash can. You want to be able to, again, know when you're uncertain which is the right action to do, and then plan accordingly if you're uncertain. So that's what we're going to try to do today. We will study an uncertainty quantification technique. It's called conformal prediction to obtain these sorts of prediction sets for black box learned models. So first we'll look at the basics for conformal prediction. Then we'll look at how we can apply it to regression problems. And the application that we look at is safety for navigation with learned perception modules. And then we look at using conformal prediction for classification applications, like for uncertainty alignment for language-based planners.
There's a question, I guess, about what if you see something that's completely out of distribution from what the classifier has been trained on?
Yeah, so ideally, so using conformal prediction, if you have an idea of the kind of environments that you're going to see, this can generalize to new environments that are from the same distribution. But if you are going to be out of distribution, these bounds are still not going to hold. So I should be really clear about that. And I'll touch on that very lightly towards the end as well. But more broadly, there are some techniques for detecting when things are out of distribution as well. And there are some other techniques for being robust to distribution shifts as well. So you can make your planners risk-aware and robust to distribution shifts. So those are both good options to be able to account for things that may be OOD.
Okay, great, thank you. And then there's one other question asking about how you generate these conformal prediction sets that you were showing for the ball, but I assume that's what you're going to be talking about.
Yes, let me just take a quick look at the question. Yeah, the orange set is defined by us. We will try to predict that orange set that I showed, and hopefully in a couple of slides, you'll know how to do it. Hence the question mark on how do you actually get these orange sets? But yes, all great questions. So let's move forward. Any other questions before I start on this? Okay. Okay, so let's consider that we have some random variable z, and we have n IID. IID meaning independent and identically distributed samples of your random variable z. We have these samples z1 through zn. Okay, so this is an unknown distribution p of that z is following, and we have n samples z1 through zn that we've observed. Assume that these samples are in ascending order for simplicity again, and that they're distinct. Both of these assumptions don't have to actually hold, but for now, let's assume that they're in ascending order and that they're distinct. So our goal is to find a q hat n such that a new sample that we get from this distribution P is less than this q hat n. Can you see that? Yes, is less than or equal to q hat n with probability at least 1 minus alpha. So that's our goal. This is our prediction set. This is what the prediction set is in this case. So again, the probability that you want to find a q hat n such that the next sample that you get of z is going to be less than or equal to q hat n with probability at least 1 minus alpha. So what does that look like? That means we're trying to find some threshold q hat of n such that z test, the new sample, is going to lie on this side of q hat of n. So how can we do this? The first idea is that, well, we have these n IID samples. We can form an empirical distribution from using these n IID samples, and then we can find q hat of n by finding the 1 minus alpha quantile of this empirical distribution. So that would be given by the n times 1 minus alpha sample of z that we've observed so far. So the ceiling, this operator that you see is the ceiling operator. Okay, so if you have, I don't know, 100 samples and your alpha is 0.9999, so it's like 100 times whatever, the ceiling of that is what z gives you. Okay. Well, you could use this to find q hat of n, but this probabilistic statement does not necessarily hold over the distribution P, this unknown distribution P, because we are only using finite samples. Of course, as your number of samples increases, you're going to approximate this distribution better and better. And so that q hat of n is going to, of course, get better and better as an approximation. But this, with finite samples, does not necessarily hold. Okay, so let's try something else. The key insight here is that we have IID samples. And the key insight here is that because these are IID and z-test, the next sample is also IID with z1 through zn, z-test is equally likely to lie between any two of these samples. What does that mean? It means that the probability that z-test is less than or equal to z1, which is our smallest sample, is 1 over n plus 1. The probability that it's between z1 and z2 is also 1 over n plus 1. Notice it's not 1 over n, it's 1 over n plus 1, because you have your n samples and z-test. So it's over the randomness of your n samples and over the randomness of z-test. That's why you have this 1 over n plus 1. So you have this probability, z-test less than or equal to z1, z1 to z2, and you can go on and so forth. you can combine these two probabilities to observe that the probability that z-test is less than equal to z2 is 2 over n plus 1. And now for any zk, the probability that z-test is less than equal to zk is k over n plus 1, okay? And as I said before, here the randomness is over your n samples and z-test. Okay. So all you have to do now is make this simple observation where you plug in, instead of k, the ceiling function, the ceiling of n plus 1 times 1 minus alpha. You may ask, why are we plugging this in? Well, because this value is greater than equal to 1 minus alpha. And so really, you found this q hat of n given by this sample from your n samples that you've observed. And this is your new prediction set. What I want you to remember really is this n plus 1 times 1 minus alpha sample that we'll be considering. And this is what's going to really inform the rest of the conformal prediction guarantees that we're going to see, that given n samples, the next sample is going to be less than equal to n plus 1 times 1 minus alpha. And by that, I do mean you're applying the ceiling operator, but I'm just approximately, incorrectly, of course, calling it the n plus 1 times 1 minus alpha sample that you've observed. And so that's it. That's how you find this q hat that completely describes your prediction set. Okay, so what have we done so far? For some random variable for which we have finite samples, they don't have to be actually IID. They just have to be exchangeable. I'm not going to go too much into the difference, but really what this means is the samples, you can have any permutation of these. You can permute these samples however you want. And so as long as that's going to be possible, they're exchangeable. But anyway, I'm not going to go into that. For simplicity, let's assume that they're IID, but actually the condition is weaker than that. We get prediction sets from a finite set of samples for the next sample. And now what we're going to do is we're going to use this really beautiful result and extend it more generally to black box predictors. So this is what it's going to look like for both regression and classification. We're going to have some pre-trained model given by f hat of x. You're going to have some calibration data set consisting of our input and the true output given by y. And given these two things, we're going to run this conformal prediction procedure and get some prediction set output that is statistically guaranteed to be correct. And that's all we're going to do for the rest. And we're going to see how this applies again to robotic tasks.
If you're going to address this already, ignore this question, but at some point, the classic question of for robotics tasks, in what cases can you make this exchangeability or IID?
Yes, yes.
Not?
So I will touch upon it towards the end, and hopefully, so the view that we're going to take here is that you have IID environments that you have samples of, and so your guarantee will hold for a new environment.
Okay.
And so instead, but you're absolutely right that this may not, if you consider a single environment and if you're considering like things that are happening over time, that this may not hold. But I'll get to how you can address that towards the very end as well. Yeah, but yes, great question. So yeah, this result actually was derived by Vladimir Vovk, Alexander Gamerman, and Vladimir Wapnick in actually the mid-1990s. So it's been a while that this has been around. The first, I think, concrete reference, if I'm right, is, if I'm not wrong, is this book, Algorithmic Learning in a Random World, again, by Vovk, Gamerman, and Schaefer. I want to point out some really amazing resources really quickly as well. There's a tutorial on conformal prediction. there's a really great review paper called A Gentle Introduction to Conformal Prediction that is constantly updated with new results as well and new insights. So it's really amazing. It's by Anastasios and Stephen Bates. And they have a set of YouTube videos also, which are really great and a really good primer for conformal prediction. And these notes by Ryan Tibshirani from Berkeley are also really great that I found really useful. I'll bring the slide back at the end so you can have these resources and you can take a look in your own time if you're interested in learning more. Yeah, so okay, I'm gonna now talk about how we apply this for like a regression task, but if there are any questions before we do that. Let me check.
Yes. So let's see. How can correctness be statistically guaranteed when there's a pre-trained neural network in the input?
Yes, great question. And okay, great. That's, I think, the best way to answer that is to look at how we can actually really do it. And it's the idea there is this calibration data set that I talked about. Okay, so let's look at that for a neural network that's a regressor, okay? So we have some pre-trained regression model. It's given by F hat. And we have some calibration data set where we have these input-output pairs. So the input is X1, that is the input that's going into the regressor, and Y1 is what the ground truth is, what's actually happened. So we define, and these, again, these are IID or exchangeable, and they're drawn from some unknown distribution. So we define a nonconformity score that gives us a measure of how well our neural network or some pre-trained regression model performs compared to the ground truth. So we define this nonconformity score by S, and we're looking at the difference between F hat of X and Y. So again, you're using your input and output label that you have, the ground truth that is available to you through the calibration data set, and you're computing the nonconformity score for every sample in your calibration data set. So for every sample in your calibration data set, you have this nonconformity score SI. You know what the ground truth looks like in your calibration data set. So really what you're doing is we're getting a measure of how well our model is performing on this calibration data set. So now really what has happened is we've transformed this problem into the problem that you'd seen before, where you have your n samples. You have your n samples of your nonconformity score, right? And now what we're trying to do is we will apply CP, and we'll get this output of a prediction set. So let's do that. So again, we computed the nonconformity score for every single sample in our calibration data set. And so we have some measure of how well our regression model is performing on this calibration data set. And now you sort these samples in ascending order. And from these sorted samples, you compute the Q hat that I showed you earlier, this n+1 times 1 minus alpha quantile, or the n plus 1 times 1 minus alpha value of your scores. Again, they're sorted, right? The sorted scores. And so your probabilistic statement in this case is that the probability that a new nonconformity score is less than equal to this Q hat is greater than 1 minus alpha. But really, what is this nonconformity score? It's just a measure of how well your pre-trained model is going to perform. It's just a measure of the difference between F hat and Y test that you're going to potentially observe. So we can plug that back into our probabilistic statement. And now your prediction set, as you can see from this statement, really is this range, F hat, that is applied to any new X, and you subtract your threshold that you've computed offline from your calibration procedure, and you add it. So you subtract and add it. So that's your new prediction set. And your conformal prediction guarantee is that in any new test sample, so the true value of what happens will lie in this prediction set with probability 1 minus alpha. Does this, anyone have any questions so far? So it's a really simple idea. And really what all we're doing is we're taking this finite sample guarantee that we just saw, and we're applying it, we're massaging it to the problem that we care about, which is uncertainty quantification for black box systems. Intuitively, what we're doing is we're seeing how well it performs on our calibration data set. And using that, we're providing a guarantee of how it's going to perform on some other sample.
Just a follow-up question on that. Is there any, the domain of X test, is that kind of limited in this scenario?
No.
Okay.
X test is just, again, it's assumed this coverage guarantee will hold if X test is sampled from that unknown distribution that we have samples for from our calibration data set. So X test, again, let me just go back, is sampled from this distribution, this unknown distribution D.
And
Thank you.
it should be separate from X train, right? So given a set of data, you need to somehow decide how much of it you're going to train on, how much of it you're going to calibrate on.
Yes, yes, absolutely. For now, I'm assuming I have some pre-trained model, but if you also wanted to train that model, then you have to be careful about this calibration data set should not be the same as your training data set, because that guarantee is not going to hold. Yes, absolutely. That's a great point. Okay, so now for some regressor, we have this conformal prediction coverage guarantee. We know how to construct these prediction sets. So let's try to apply this to the perception-based navigation task that we discussed earlier, where you may have some sort of off-the-shelf perception module that's making predictions about where objects are in the environment, but you have no idea what kind of distribution of objects it's been trained on. So you want to use this technique and use your calibration data set to get an idea or get a sense for how well this system is going to perform for new environments that you're interested in. Okay, so again, this is the setup. We have a quadruped that's trying to navigate through this office-like environment. There's a camera on the quadruped that's making observations, and it's making predictions on where the objects are in its environment. These predictions may be off, they may not be exactly right. And so I'm over here comparing it to the actual location of the obstacles, of the objects. And the goal is, can we obtain some sort of an assurance on our perception system so that we can actually use it in conjunction with our safe planner, so we really have an end-to-end guarantee on safety. You know, in such environments, based on what state the robot is making an observation for, there may be occlusions, so over here you can see that, oops, these chairs are not totally visible, and we want to be able to account for all of these things that do happen in the real world as well. We also account for a limited field of view as well in our calibration procedures. So let's, oh yeah, I have that in there. But yeah, let's just get started and look at what this non-conformity score will look like for perception errors. Again, assume that you have access to some calibration data set where you know the actual location of the object. And now you're also making a prediction, given this observation, of where the perception module predicts the objects are. So I'm going to denote the union of these bounding boxes that are being predicted by our perception module. And I'm going to call these union of bounding boxes predicted by the module B. And I'm going to call the actual location of these objects and the union of all of those bounding boxes to be A. We want to find the smallest inflation that we need to make to our perception prediction such that our ground truth locations lie completely within this inflated output. And we want to find the smallest such inflation. So you can imagine what this means is if you have a bounding box, you're inflating its length, width, and height by some amount, and you want to find the minimum such inflation that you need to do. And that's really a notion, again, of your perception error. How far off are the predictions compared to the ground truth? And you want to find this minimum inflation. And that's your nonconformity score. Couple of things that are unanswered here or unclear here. The score that I'm showing you is for a single observation from a single state. So it's unclear what the calibration data set really is here. So let's take a look at a couple of options that we have for making up our calibration data set. Okay, so the first option is that we collect the perception errors from all locations in a given environment, and then all of these different perception errors that you see form the different nonconformity scores. And now you perform CP, your usual conformal prediction procedure on top of that, and find some sort of inflation that you need for a new perception output. This is great because now you have a guarantee on your new perception prediction set or your calibrated prediction set. But the not so great thing is that it's only going to work in one environment from some state, from some other state in the same environment. Ideally, we would like to run our perception modules in all sorts of different environments. So let's consider a second option. Let's consider many different environments, and we're considering now IID environments instead of IID states. And for each of these environments, let's consider the average perception error for each of these environments as our nonconformity score. Now, the new guarantee is going to hold across all of these different environments. So let's apply this and see what happens. So here, the quadruped is going through this environment, and these red boxes that you see are the predictions that are calibrated using conformal prediction, using the nonconformity score on average across different environments. You can actually see even here that these boxes are not quite right. So what's going on here? Why are these predictions still not quite right? And again, when you use this in conjunction with a safe planner, the orange region that you're seeing is the free space that's being predicted. You can see these true locations of our chairs are being classified as free, are being detected as free. And so that leads to a path that's planned through the chair, so it leads to a collision. So it's still not totally safe. So what's going on here? What's happening is that the distribution of states that are visited by the planner is not the same as the distribution of states we considered in our calibration data set. What does this mean? Maybe you gridded up, you uniformly sampled points in your state space, and you computed the perception error from each of these points, or maybe you discretized your environment and then you chose those samples. Maybe you discretized it this way, and from each of those locations, you computed the perception error, and you then deployed this on the robot. And what would happen is that the planner would actually not visit all of these states with the same distribution. The other thing you could do is you could collect a set of trajectories in every environment. You could run your perception plus planning system, and you could look at the states that are visited by your robot. But then what happens is that when you find the calibration, your perception error, and you calibrate your system, you inflate your perception system with this calibration. Again, when you use this in conjunction with your planner at test time, you're still going to visit a different set of states, a different distribution of states than when you use the uncalibrated perception system in conjunction with your planner. So this is always going to happen. There's always going to be this distribution shift. And the last thing is actually something that you're not seeing here. It's something that also holds with this sort of an approach to conformal prediction in this case, is that you won't be able to make any changes to your planner parameters if you used your planner to collect your calibration data set. So ideally, what you would want is something that's robust to this closed loop distribution shift, is what we call it, that you end up seeing for this application and in general. So yeah, so we have this guarantee across environments, but this is not robust to closed loop shifts. So we consider a third option where we collect the perception errors across many different environments, but now we look at the worst case perception error in every environment. So what is going to happen is that this is going to be a guarantee across environments. So this will hold in a new environment, and this is going to be robust to any state in a given environment. So you're collecting your perception. Yes.
When you're talking about any state in the environment, so
Yes.
you showed us one perspective and then you gridded up that perspective and you
Yes.
talked about the different regions. Are we thinking about state in terms of the image space of one? Or are you talking about state as in the robot at different states and the view that it gets from those different states in the environment?
Yeah, I meant the robot state. And I want to be clear also, it's going to come up in a couple of slides, but we consider a sampling-based planner, and we have a set of states for the sampling-based planner that can be visited. And we're using the same set of states that we've sampled for the sampling-based planner for our calibration procedure. So whatever set of states your sampling-based planner can visit across different environments, you consider the same set of sampled states, really, for this application. And then you consider, yes, what is the perception error from each of these states? And you consider the worst perception error across different environments.
Okay, thank you. And then I think this is a slightly delayed question. Apologies. This is just someone trying to make sure that they understand that you have a pre-trained perception system.
Yeah.
And you are now integrating the assurances into that using this calibration.
Exactly.
And how important is it for the the training distribution to be good? Like, can you handle a decent shift from the training distribution and test by having a good calibration?
Yeah, I think all that matters is that your new environments that the robot is going to see are sample IID from the distribution of your calibration.
One. Yeah.
Yes. So what it's trained on doesn't really matter. What will happen is if that distribution that it's trained on is totally different, the perception errors will maybe be higher than you'd like. And so the inflation that you're going to end up seeing, it will be more, which is not great. So ideally, you'd like a good perception model, but we're able to account for it if it's bad as well. And you're able to be safe, but maybe it's more conservative. Yeah.
Thank you.
And at the same time,
Yes.
sorry, just one doubt in the previous slide. So this option 3 is like kind of making the system more conservative than option 1 and 2 to kind of guarantee the safety. Is that the case?
Yes, actually, and I don't have this on the slides. I will get to the conservatism in a bit, but for option 2, if you look, when we did this across a bunch of different environments for our applications, we had an inflation. So we needed to inflate the perception output of some off-the-shelf model by 0.5 meters on each side. No, wait, 0.05 meters on each side, if I remember correctly. And for option 3, it was 0.7 meters. So it's
Right.
quite a bit of a difference. But the reality is the guarantees with this don't hold because of the closed loop distribution shift. So that's the problem that we see.
But
But you're
but
absolutely
isn't
right that yes, it's more conservative.
but isn't there a possibility that these inflations might become too high, that uh, since we are considering the errors across the environment, that one environment has very small inflation error and the other environment has very large inflation error, which results in kind of unreasonable conservativeness?
It could, and you could potentially have over your distribution. Yes, you could have higher perception errors, but that's also, I think, indicating that maybe your perception model is not performing as well from all of your states as you'd like. So there is that as well. So it's maybe signaling that the performance is not good. But you're right that it is more conservative, and we will talk about how to address that in like 2 slides. Yes. Okay, so really coming back to this picture, what we're doing is we have some now red prediction from our perception module, and using this calibration procedure, we're now predicting inflated bounding boxes that could potentially be more inflated than we'd like. In this case, these are the blue boxes. But we have a guarantee from every state that these inflated boxes will contain the ground truth location of our object with probability at least 1 minus alpha, right? So let's see this in our application. You can see now that the predictions are always right, but they may be a little larger, like you said, than you'd like. So what do we do? Is there a way to make this inflation less conservative? Yeah, there is. The nice thing about the guarantee that we have is this holds across all states. So you can actually consider the union of your free space over time or the intersection of your occupied space over time. What does that mean? At time t equal to 0, the robot is predicting these light red bounding boxes, like I'm showing the union of all of these bounding boxes. Given its observation, it has a limited field of view as well. So this blue part is the free space that it's observing. Okay, given its field of view, given the fact that these large obstacles may also have occlusions behind them. So we are only expanding our free space into what we can see, right? And these red boxes, the darker red boxes, are the ground truth locations. At the next time step, you may see a different set of larger boxes, but both of these are true. Both of these hold because of our robustness guarantee. So now the union of the free space over both of these time steps is correct. And similarly, the converse way of thinking about this is that the intersection of both of these occupied spaces is necessarily right? So this is a filter that we're applying, and over time, you will become less and less conservative, which is really nice. And that's because you're not doing this average, you're doing a robust guarantee. So yeah, I mean, as you can see then over time, these boxes have really converged, right, to the true location of the obstacles. So the robot is able to successfully navigate while being safe. And I'll add a quick point to our safe planner. You can use this in conjunction with any sampling-based safe planner. We use fast marching tree star, and we also account for the dynamics of the robot, which we compute through SysID. And we also account for the states from which no action will lead to safe behavior. It's called the inevitable collision set. So we are able to account for safety in an end-to-end manner. So yeah, so this guarantee holds with probability 1 minus alpha for new environments, sampled IID, for a new environment sampled IID from the calibration distribution. And you can see here, right, like this free space has really expanded to the edge of the obstacle because of the filter that we're applying on top of our inflation. So over time, the conservatism gets smaller, I would say. But could we do still better? Yes, the answer is yes. And this kind of alludes to or relates back to Sylvia's earlier question of like, what if you want to use part of your distribution, part of your calibration data set to also further train the model. You could maybe fine tune it, maybe an off-the-shelf perception model to fit better to the environments that you're interested in. So then you could take a calibration data set, you could split it into two parts, S1 and S2. You can do this because the calibration data set is exchangeable. So you can really split it any way you want. And you have two sets, S1 and S2. So for this first set, you can fine tune it. You can make it better for the type of environments you're interested in. And then using the second set, S2, that's where you perform your usual calibration procedure that I've shown you so far. So now your F-hat, your regressor, your object detection module is this fine-tuned model that you're using, and it's fine-tuned in S1. And now your guarantee here depends on the size of S2 that you're using. And so this holds because your data set is exchangeable, and this method is called split conformal prediction. Okay. So I just showed you one way to think about conformal prediction for regression applications for perception and planning. And this gives us a rigorous end-to-end guarantee in new environments. But really, you could apply this to any regression task that you'd like. Okay. I'm going to move on to classification next, but I'll pause for questions if there are any. Okay, great. Let's move on. Okay, so now let's think about the same setup, but for a classification problem. Again, it's the same thing that I showed you before. You have some input of a pre-trained classification model. In this case, your F-hat is maybe the softmax score associated with the classes that you have. And you again have a calibration data set where you have these input-output pairs. Your X1 through Xn is your input. Y is now the true class that you care about, the ground truth class, okay? So your nonconformity score now is different from what you've seen for regression. Now it is defined using the softmax output of the true class. So Si in this case is 1 minus F-hat of X, Yi. Yi is the true class. So the softmax score associated with the true class. So observe here, if your nonconformity score is high, this is when your classifier is performing, again, poorly. So again, it's a measure of your classifier's performance. And when that means that your softmax output is low for the true class, which is not great. And again, we want to use the same procedure that we've seen to get a prediction set. Okay, so now you've collected your nonconformity score using 1 minus the softmax score. In this case, it's a softmax output of the true class. This is 1 minus Si, it's just this, right? It's F-hat is equal to 1 minus Si. So don't worry about what this means. Again, your nonconformity scores, you arrange them, you sort them, and you arrange them in ascending order. You get the quantile that you care about, the Q-hat, again, n+1 times 1 minus alpha. And again, it's the same sort of guarantee that we've seen before. The new nonconformity score is going to be less than equal to this Q-hat with probability at least 1 minus alpha. Now, your prediction set is the set of all the predicted classes that have a softmax score above 1 minus Q-hat. So you computed this Q-hat using your calibration data set. And now you use this threshold to see, okay, which of my softmax outputs for a new test environment are above this threshold that I've computed. And now I have a prediction set of the possible classes that could possibly be right. So your conformal prediction guarantee is again the same. Probability that the true class lies in the set that you're predicting, the set of classes that you're predicting, is more than 1 minus alpha. Right? Well done. Okay, so let's try to apply this to some language instructed planning tasks. Let's go back to the same example that we started out with, where the human says, place the ball in the microwave, please. And we ask the LLM to generate plans. You may be wondering, like, how is this a classification problem? Well, one, again, we care about the safety in this case, but two, the challenges here, as I said before, our LLMs tend to make mistakes. There are mistakes. There are often uncertain instructions given by humans. We want the robot to ask for human help when it's not sure of what it should do. And we want to somehow convert this, as I alluded to earlier, into a classification problem. So the question is, how do we quantify the uncertainty of our language-based planner? We tell the LLM, give me a set of possible next steps. So turn this problem, this LLM-based prediction, into a multiple choice question answering setup. And you ask the LLM in this case, what are some possible next steps given this user instruction and given what the robot is observing in the environment? Associated with each of these possible next steps are the next token probabilities of which one is right. And now you can use this classification setup that you've seen for conformal prediction to calibrate the uncertainty of your large language model planner for the kind of tasks that you care about for your robotic application. And in this case, the nonconformity score is given by the next token probability of the right action amongst all of these possible actions. So in this case, the right thing to do is put the plastic ball in the microwave. So you collect the nonconformity score associated with this next token probability.
So quick question, the LLM is generating ABCD? Is that right?
Yes.
Okay.
And LLM is also giving you this next token probability. Yes. Okay, so what does your calibration data set look like in this case? In this case, you have a set of different sorts of human instructions, and you collect the true label in all of these different setups where you ask the LLM to say, generate a set of possible next plans. You manually label which one is the right thing for your calibration data set. And now you collect, as you've seen before, this histogram of nonconformity scores, and you arrange it, as you've seen before again, in ascending order. You find the associated threshold with the nonconformity score, and you have your guarantee on your prediction set. What does that look like in action? The human says, place the ball in the microwave. There's a context that, okay, there is a microwave, there's a landfill bin, a recycling bin, and a compost bin. The robot makes observations of, I see a metal ball and a plastic ball on the counter. Using all of this, it generates the possible next steps and the next token probabilities associated with all of these. Given the offline calibration that we've done, we know that the prediction threshold, CP-related threshold, is 0.21. So that's the Q hat that you get from your prediction CP procedure. And now you include in your prediction set any possible next step that has the next token probability that is above this threshold. Sorry, excuse me. So your coverage guarantee at test time is that the probability that the right thing to do, the correct plan, is in the set is greater than 1 minus alpha. Great. But now there are two possible actions here, so the robot doesn't know what to do. So it says, which one should I pick up? Excuse me. And the human then tells it, okay, you should be picking up the plastic ball. So let's see this in action. I'm not sure if you're going to be able to hear the.
Hey, robot,
Can you hear it?
could you put the bowl on a small counter in the microwave?
Should I pick up the metal bowl or the plastic bowl?
Pick up the plastic bowl, please.
So question, the number of options that it chooses, 4. Is this
Mhm.
something that's preset of choose between 4, or is this variable, and how is that decided?
Yeah, so right now we have 4 options and there's a 5th option E, none of the above, which could also potentially happen that none of the options that it's generated are right. Yeah, it just needs to be consistent
Mhm.
across your calibration data set and at test time. You
Mhm.
could have any number of like plans that you like, and that should be fine. Yeah.
Here,
Okay. So maybe a question that you're thinking of, certainly a question that we were thinking of is the robot just gonna, a terrible policy here is just ask for help all the time, right? Well, no, the nice thing about conformal prediction is that it achieves a minimal average prediction set size. The caveat there is if your F hat is accurate. So the answer is depends on how good your LLM is, how often it's going to ask for help. Okay. So yeah, this is one of the applications that we have for applying conformal prediction for classification applications. We've also, I only showed this to you for a 1-step setting, but you can also extend this, as you can imagine, to a setting where you have multiple steps and you're taking actions. The robot is taking actions over multiple steps. Okay, so some things to consider. You could call this the dirty laundry, what have you. You should be, I would say, when you're trying to use these sorts of uncertainty quantification techniques, like conformal prediction, you should be, I think, a little careful about how you collect your calibration data set. And I think it's worthwhile to think about how does this affect the guarantee that you're getting? What kind of a guarantee are you getting? So I showed you 3 options, right, for the perception-based navigation tasks. And I just want to come back to that over here. If you consider just one environment and assume this is some sort of a state space gridding, but you gridded that up and you had some sort of guarantee across the different states, then this is only going to hold in that environment. Same goes with the set of trajectories, right? If you collect a set of trajectories, you may be seeing when you apply your calibrated learned module in conjunction with the rest of your autonomy stack, you may start seeing these sorts of distribution shifts in closed loop that you may not have accounted for in your calibration pipeline. So that's something you should keep in mind as well. A bound across environments probably also means that you are collecting more data for your calibration, and it may be more intensive. So that's the one other thing that I would say differentiates between these 2 types of equally valid ways, I would say, to get a guarantee. But just think about what kind of a guarantee you're getting. Something else that you should think about is the data that you're seeing really IID? Is the calibration data set really exchangeable, or is it valid, right? How are the robot's actions affecting the guarantees that we have? You could imagine that maybe the human is maybe you have like a human robot interaction setup. Maybe over time, the human is adapting to how the robot's behaving, and that maybe leads to a set of interactions that are not quite from the same calibration distribution that you've considered. There's the way to maybe think about this and how things change over time is one of the approaches that I've seen recently. It's an adaptive approach to conformal prediction, where you have really an online learning kind of a view of conformal prediction, where you're updating this alpha, the confidence that you care about, based on how well your learned model is performing and what you're seeing over time in the environment. But this, I will warn you, is a slightly weaker guarantee than the original conformal prediction guarantee. It holds an average. And yeah, so this is the paper that's associated with this adaptive approach to conformal prediction. I would highly recommend that you give it a read. We actually applied this idea from Gibbs and Candace to an adaptive approach to motion planning in the presence of like dynamic agents, where we were predicting over time what sort of trajectory dynamic agents would have, and then we were adapting for it using MPC. We were also predicting multi-step prediction sets for this was like an MPC based split. So yeah, take a look at that as well if you're interested in how to apply this to dynamic environments in a single setting, in a single like rollout in one environment as well. But I will warn you again, the guarantees are slightly weaker than what we've seen so far. And the last thing to consider is this notion of marginal versus conditional coverage that I haven't talked about at all, but is quite important. The guarantee that I showed you holds for a single test event, for a single new sample from your distribution. So every time you want to draw a new sample, you need to get a fresh calibration data set. Maybe that's fine if you have a guarantee across environments and you're running it in a new environment. But this is also something that you want to consider, that this is a marginal guarantee that holds with the randomness of both the calibration, this data set, and the test event. There is a conditional guarantee that holds for most, because for most practical applications, you really only want to collect a calibration data set once and be done, and then know how this is going to affect the kind of bumps that you're going to get. So really what happens is there is a result, again, I think by Wolf, that I should have maybe cited here, but that says that for any new, you can apply this condition on just the calibration data set. So this is going to hold in general, but observe that this is a probabilistic statement about your prediction set. So this is a statement that's saying, oh, my prediction set is going to be right with this probability distribution given by a beta distribution. And that also depends on how large your calibration data set is. So the size of the calibration data set also affects the performance again that you're going to see when you deploy this. Okay, so some concluding remarks. I mean, we are really increasingly relying on learned models for autonomous systems. And I mean, this is great because you're gaining, your robots or your autonomous systems are gaining new skills. They're becoming more agile and adaptable. But I think it's really important to also think about what you may lose in the process, which I think is safety. And since this is a class about safety, I'm sure everybody agrees that safety is really important. So I think it's really important to think about principled ways in which, you know, you can use these learned models without sacrificing safety. I think conformal prediction is just one of these many ways. But yeah, that's all I have. And I'll leave you with these resources, as I promised earlier, the original reference to conformal prediction, some great resources in my opinion to learn more, and the two papers that we discussed today.
All right, wonderful. Thank you so much.
Yeah, thank you for
That
having me.
was really wonderfully done of the tutorial, the cool research, the dirty laundry, and things to consider, the next steps, and the resources. Thank you so much for providing all of that. We have time for maybe one, maybe two questions. Any from the audience?
I had one. By the way, thanks a lot for the presentation. I had one, like, I mean, from a bird's eye perspective, like, would you consider that you're trying to use methods from statistical learning on top of like the learning-based methods which are there right now to kind of give some like guarantees? Would you consider that as like the overall bird's eye view on your work?
Yes, that's exactly right. So what we're really trying to do is we're trying to use all of these great learned models that we have, but we're trying to use a statistical perspective on how well they're going to perform for tasks that we care about. So it's really taking some sort of a black box model, but also then having some sort of an understanding of the uncertainty associated with it for the tasks that you care about. Absolutely. So I agree with that statement completely.
Thank you.
Any last questions before we? I know we asked many during the talk, so. Okay, most of my questions you then answered in your next slide, so this was perfectly done. Thank you so much for taking the time to talk with us.
If anybody has any other questions, feel free to email me as well. I'd be happy.
What do you know your UCLA email yet? Is that active or what?
No, I don't. I can give you my Princeton email,
Okay.
which I have for the next couple of months, but
Okay.
I will update my website with my new email.
Sure.
Well,
Okay, wonderful. So yeah, people can check there.
yes.
All right, wonderful. And then everyone, please do check out these extra resources for conformal prediction. All right, and with that, I guess we will close it out for today. Thank you again.